This module continues our exploration of anti-collision concepts, forming sub-module 2 of 3. Anti-collision is a critical process in well planning and drilling operations, designed to prevent the intersection of well bores in increasingly crowded fields. As multiple wells are drilled from shared locations such as offshore platforms or onshore pads, the risk of well collisions grows. A collision could compromise well integrity, cause production losses, or lead to catastrophic safety incidents. This session will build on the foundations covered in sub-module 1, delving deeper into the tools and methods used to quantify uncertainty and assess separation between wells. We will introduce concepts such as the separation factor and ellipsoid of uncertainty and review how these are used in practice to ensure safe drilling margins. You will also be introduced to visualization tools like spider plots and traveling cylinder plots, which allow engineers to model risks more effectively. By mastering these tools, you will develop a greater ability to evaluate positional uncertainty, understand collision risk, and apply these techniques in planning, monitoring, and executing safe drilling operations. This introduction sets the stage for the module objectives. The objectives of this module are structured to give you a comprehensive understanding of anti-collision practices and how survey accuracy underpins safe drilling. By the end of the session, you should be able to explain the causes of survey inaccuracies and outline methods for detecting and correcting them. You will gain familiarity with important terminology such as the ellipsoid of uncertainty, EOU, which represents the possible error envelope of a surveyed point, and the traveling cylinder, which provides a practical way to model clearances between wells. You will also learn to plot well trajectories, calculate separation distances, and apply the concept of separation factor to evaluate collision risk. The module emphasizes how anti-collision plots are generated and interpreted, including spider plots and other visualization methods. The separation factor, SF, is a central metric in anti-collision assessment. It quantifies the margin of safety between a subject well and an offset well by comparing the center-to-center distance to the size of the uncertainty envelopes, particularly the semi-major axis of the ellipsoid of uncertainty. Different thresholds categorize the level of risk. When the oriented separation factor, OSF, is above 5, wells are considered safely separated. If the OSF falls between 1.0 and 1.5, it indicates minor risk requiring close monitoring and possibly corrective action. An OSF of less than or equal to 1.0 is deemed a major risk, and drilling must be halted to prevent potential collision. This framework ensures operators evaluate risk consistently and conservatively. SLB developed the concept of the OSF to provide a standardized measure that accounts for directional uncertainty. The separation factor highlights how even small inaccuracies in survey measurements can significantly reduce confidence in well positioning. Therefore, understanding and applying SF values is essential for safe decision-making during both planning and real-time drilling operations. In this slide, we are introduced to the concept of the ellipsoid of uncertainty, or EOU. When we drill a directional well, every survey point we take is influenced by measurement errors and tool limitations. The EOU is a way of expressing that uncertainty visually and mathematically. Instead of imagining a single exact point where the well bore lies, we represent the location as a three-dimensional ellipsoid. This shape captures the range of possible positions the actual borehole might occupy. The EOU is defined by three axes. The major axis is typically aligned with azimuth and is the largest source of error, largely due to the limitations of magnetometers and their susceptibility to interference. The minor axis reflects inclination uncertainty, and the vertical axis represents uncertainty in measured depth. Together, these axes create a volume of probability around each survey station. What this means in practice is that when we plot well paths, we don't simply look at a line, we account for this uncertainty envelope to understand potential overlap with nearby wells. Continuing, we now focus on what contributes to its size and shape. Survey sensors, no matter how advanced, have limited precision. For example, magnetometers can be affected by local anomalies in the Earth's magnetic field, or by interference from nearby steel in the drill string. These external factors add to the uncertainty of azimuth measurements. The ellipsoid represents the range of possible positions of the wellbore at a given survey point, typically expressed as a probability boundary. Most often, we describe this with one standard deviation, or 1 sigma, which equates to a 68% probability that the true well position lies inside the ellipsoid. In other words, about 2/3 of the time, the well's actual path will fall within that space, assuming the error model is accurate. In directional drilling, this is essential for anti-collision work. When planning wells in close proximity, we need to recognize that the plotted centerline does not guarantee the borehole's exact location. Instead, we must respect the EOU as the real footprint of uncertainty. By incorporating these tolerances into our planning, we reduce the likelihood of unexpected wellbore proximity or intersection. This slide introduces tool error models, which help us understand and quantify how measurement errors affect wellbore positioning. In practice, every sensor we use, whether magnetometers or accelerometers, has inherent biases and limitations. Over the years, several models have been developed to describe how these errors accumulate and propagate along a well path. The cone of uncertainty model was an early approach, giving a simple visual representation of positional uncertainty as a widening cone. The SESTEM model then attempted to refine error understanding with more detailed mathematics. Later, Wolf and DeWart developed a more comprehensive framework that integrated different error sources, from sensor bias to environmental influences. Today, the ISCWSA error model is the industry standard. It is widely accepted because it uses agreed coefficients to represent tool accuracy and environmental influences in a consistent way across the industry. This allows survey providers, operators, and regulators to speak the same language when evaluating positional uncertainty. The purpose of these models is not to eliminate error, but to quantify it realistically so that we can calculate uncertainty and assess risks, such as well collisions. Understanding which model is being applied is vital when interpreting survey data. Comparing several different visualization tools used in anti-collision analysis. The spider plot, as we've seen, provides a plan view of all wells in a field or pad, highlighting zones of proximity. The travelling cylinder plot is another tool which presents a polar view showing how a subject well passes relative to offset wells as it advances. This helps visualize clearance in a circular perspective, almost like looking down from above. Then we have SLB's directional drilling toolbox, which integrates survey and planning data into a digital platform, making calculations and visualizations more accessible to the directional driller in real time. Finally, there is three-dimensional visualization, which provides the most intuitive perspective by displaying all wells in 3D space. This makes it easier to understand true separation and collision risk. Each of these tools has strengths. Spider plots are simple and effective for planning. Travelling cylinder plots give detail on proximity. Digital toolboxes combine data in one interface. And 3D visualization provides the clearest understanding of geometry. Together they give drilling teams the confidence to plan and execute wells safely, especially in congested fields with many offset wells. The spider plot is one of the key tools used in anti-collision planning. What you see on the slide is a plan view of the structure, where multiple well paths are displayed together. Each line represents a subject or offset well, and the overlay of EOUs allows us to visualize safe or risky areas. The spider plot is powerful because it allows directional drillers to see the big picture, all planned and executed wells in relation to one another. It also allows zooming into problem zones where well bores may pass close to each other. One important point is that the intersection of two well paths on a 2D plan view is not always the closest approach because true separation is three-dimensional. However, the spider plot is still an effective planning tool for identifying potential conflicts early. The key takeaway is that two wells must never cross at the same true vertical depth. If they do, a collision is inevitable. Here, the spider plot is shown in more detail, focusing on the relationship between a subject well and an offset well. In this example, you can see the subject well plotted vertically in green, while the offset well is plotted horizontally in red. Along each trajectory, true vertical depth markers are displayed. These depth markers are crucial because proximity between wells must always be assessed at the same TVD. Even if wells appear to cross on the plot, they may not be close in depth. Conversely, two wells can be dangerously close if they approach the same TVD at similar coordinates. By comparing EOUs around each survey point, the spider plot highlights where there is risk of insufficient clearance. This gives the directional driller and the planning team the information needed to adjust trajectories before drilling proceeds. What this reinforces is that spider plots are not static drawings but dynamic tools for assessing safe separation. Ultimately, this tool provides clarity in planning by showing relative positions of subject and offset wells in both map and depth views. We return to the objectives of the module. Firstly, you should be comfortable defining the ellipsoid of uncertainty and explaining why it is central to survey interpretation. You should also understand the concept of the travelling cylinder, another important anti-collision tool, and how it differs from a spider plot. Lastly, we have begun to explore various methods for plotting wells and calculating separation, whether in plan view, polar view, or 3D space. This concludes Submodule 2 of 3 on anti-collision. Please progress to the quiz. Thank you.